of x, that's really one function f of x times another function g of x. And just as like a quick example of what that might look like, maybe my k of x was like 3x squared plus 1 times sine of x. So in this example, f of x would be the 3x squared plus 1, and g of x would equal sine of x. And you might optimistically think that when we take the derivative, we just have to take each derivative separately and multiply them together. Unfortunately, that's not what happens when we actually use our limit definition of the derivative. So we'll just kind of hold on to this as an example to come back to. So generically, this is going to be my good morning, come on in. So generically, this is going to be my function k of x f times a g. In terms of our limit definition of the derivative, just going to remind everybody, that means I'm going to be looking for the limit as h approaches 0 of k of x plus h minus k of x all over h. And I will say that in office hours on Tuesday, I had people asking me about the other limit definition of the derivative as x approaches a, and we can definitely do some of that in office hours if people want. This one's going to be a little bit easier for us for the product rule. So I'm going to stick with this one. Well, this means that everywhere I have an x in my k of x, I've got to replace that with x plus h. So I am looking at a limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x, whole thing over h. Now here's the fun part. A couple hundred years ago, the mathematicians stood around and stared at this thing for a while. And some dude was like, oh, I know how to work through this. I just have to add 0. So this creative mathematician probably like got his PhD for that or something. I should go look up the history on that. I'm just making it up. But yeah, he was like, we can solve this by adding 0. And here's the way that he added 0. He took that f of x plus h times g of x plus h, and he subtracted off f of x times g of x plus h. And then he added it right back in. So that these two things together add up to 0. But I don't want to forget that part. We still had that part. It's kind of like we just scoot it over. And then this whole mess is over h. And if you're thinking to yourself, that got worse, not better, you're kind of right. But now we're going to help it to get better. And really, what this mathematician did is he looked at this and said, I'm just going to regroup this into 2 separate pieces. And that grouping is kind of going to look like this part, and then this other part. But because that h is the denominator for the entire thing, that means the h is the denominator for this part and also for this part. And I'm gonna write out a couple of extra steps here. So I'm going to group all this stuff together. So I'm going to have f of x plus h times g of x plus h minus f of x times g of x plus h all over h. And then plus f of x times g of x plus h minus f of x times g of x all over h. clever mathematician looked at that and said, hey, now that I've regrouped these, there are some things that I can factor out. So from the first pairing, I can factor out a g of x plus h. And from the second pairing, I can factor out an f of x. So I'm going to do that so that I've got a limit as h approaches 0 of f of x plus h factored out of g of x plus h. Oh, sorry, that wasn't what I was factoring out. I was factoring out g of x plus h. I underlined it. I just wrote the wrong thing. Factoring out a g of x plus h. So I'm left with f of x plus h minus f of x all over h. And then over here, I'll get it right this time. I underlined that f of x part. That's what I'm factoring out. And then I've got g of x plus h minus g of x all over h. And technically, all of this is still inside of that limit. We're taking the limit as h approaches 0 of the whole thing. So now I'm actually ready to deal with the limit. Well, if I plug in 0 for h right here, I end up with g of x. And if I take the limit as h approaches 0 of f of x plus h minus f of x all over h, well, that's just our definition of the derivative for f. So that is f prime. Here at the back, there isn't even anywhere for me to plug in the 0 here. So it is just f of x. And then all of this mess, g of x plus h minus g of x all over h in the limit as h approaches 0 is our definition for g prime of x. Now, I think it is highly, highly, highly unlikely that you would have to show this on a quiz or an exam, right? But that's where our product rule comes from. The upshot of this, the part that really we are going to use over and over again, is kind of this thrilling conclusion piece. And I'm going to summarize it a little bit differently and say that if I have f times g and I take the derivative, I get f prime times g plus f times g prime.